Right, so we'll have a look now at our indices and see how they're going. So what is it about indices? Similar kind of thing. What is the recognition? What is the intuition? Well, obviously, what is an index? What do we say an indice is? Well, we all know that it means this. That's for one thing. Perhaps a harder thing to do, which I did do in both of the workshops, was it's a shorthand notation for multiplication. So in that way, when we think about an index, we don't want to be befuddled by it. One of the things we also know is that we generally tend to see things with the hidden index of 1. We don't do well at doing that, but the index of 1 is important. So we're going on with the indices. If we take an A2 times an A3, very straightforward. Oh, we can do it the long way and then bring all of them together. And so what we would do at school is we would jump straight in and would say, that's 1, 2, 3, 4, 5, A5, easy peasy. Okay. Now, here's the bit at university that we need. The bit at university requires us to understand change of form. So there's that strategic intent again. The change of form is simply that here we can write the indice sum. Now that's the bit that gets left out, I think even up to year 10. So students are very good at the other bits, but putting this bit in. Now, urgently and importantly, what happens at university? We're expected to go backwards in our recognition of the forms. That is 2 forms of the same thing. 2 forms of the same thing. Wow, okay, that's amazing. 2 forms of the same thing. So let's think about that. Let's just have a look and see what we saw here. 2 forms of the same thing. And I may have even taken it out, believe it or not. Some of us were interested in having there you go, that's the one. 2 forms of the same thing. So what do we do with our sums? There's one, just like what we're doing. A half PA by 3 PB. A half PA, 3 PB. So that's a bit more surrounded with some complexity. But it says multiply them together. So that's our question. How is this different really from A2 and A3? Well, it's different in that there's pronumerals there, but the concept is not going to change. Okay, the concept is not going to change. In effect, we're doing a half times 3, so it'll be a half 3 on 2. Let me write it as 3 on 2. And then we'll have our PA and our PB. So there's our side-by-side pair. So what this is suggesting is that there's another form. 3 on 2, P to this form. So changing forms. And in this case, it's A plus B. The fact that it's pronumerals is irrelevant. The concept is exactly the same. Over here we had 2, over there we had 1. So this is the one that we're looking for, 3 on 2P and the sum. 1.5, not 3.5. Okay, so that's the one that we're looking for there. 2 questions out of the MRS that are not well done. That are not well done. And now I believe you're beginning to get a bit of an understanding into why that's the case, that they're not well done. Okay, so in this way, what we'll be doing is just continuing on teaching you the long way and helping you to cognate the importance of changing forms. So I'm going to do a rather complicated thing that you'll do, in Maths 1, and I'm not doing that for the reason that we'll do Maths 1 work. I'm doing it for the reason that I don't want to teach you rates. I really don't. It's proportional to n. But I want to unpack this because I want to see this happening. and I want to see this happening because you've got to see it. That's my purpose in doing this. So in a way, I don't care whether or not you can do this. It doesn't matter to me. This is a rate, is a number. I did a little demonstration in, where we had people walking, and one walked at that rate, another one walked twice the rate, another one at 5 times the rate. So we had kind of 1, 2, and 5, and all that did was determine our walking pace. When we put this into an equation, the rate of change of the population, the number, is proportional to the actual population. So the bigger the population, the bigger the number. So in this case here, if we were going to put this into an equation form, it would be something like a constant for a particular context, and n. So what we're going to do there is recognise the concept of this system and then do what's called separation of variables. And it doesn't matter if you don't know how to do that. I'm just helping you through the initial idea. So the first thing we'll do is we'll put the t's and the n's together. So we'll have 1 over n dn. How did I do that? Divide by n. What you do to one side, you do to the other. And multiply by dt. So there I've got my t's on one side and my n's on the other. The next thing I'll do, of course, is integrate them. And this has a particular form. We'll learn about that in the coming weeks and integrate this one. And this straight away brings us to another idea. What's in the gap there? I can bring the constant across because it's not a function of t. Very interesting. So if we do this here, we're going to get the ln of n. And we'll put the c over the other side. And this one will just become kt with the c inclusive. Now, how do I undo ln? I take e to the ln. What you do to one side, you do to the other. Oh, watch out. All of a sudden we have a summed index. So when I asked in the lectures about this next step, this is where students were, well, I don't really understand what the next bit is. But we did it up here. P by P became P. So we're going backwards in this separation of variables problem. We're going that way. Same here. We've got this one and we're going that way. So if we've got an A, we get 2 A's. If we've got a P, we've got 2 B, 2 P's. So if we've got an E, we've got 2 E's. Oh, I see. One of them is a KT and one of them is a C. Now it turns out that we can put the constant, that's just a number, and we like to substitute the constants that way. Now you've seen that equation before, but the important point was going between this step and this step. If we can take away some of the pain that comes with learning new material by simply remembering our intuition and our education on some of these ideas, that's purely an indice idea, as you can see. So that's a big idea, but it's a simple idea, isn't it? It's just a simple idea that needs some recognition. All right, what about other indexes? I mean, I could go on and, we could do 8 to 100. Don't know that there's too much value in that. We've seen how we can multiply and sum them. There are subtractions and things, but I won't labour that at the moment. I've already mentioned A1. What about A0? What about A0? A0 is 1. Wow, okay. So what about Jason to the power 0? What about car to the power 0? What about some expression to the power 0? Or a number to the power 0? Or some rather complicated thing, all raised to the power 0? They all mean the same thing, 1. And so this is another recognition of forms. It's a recognition and the changing forms. Anything raised to the power 0 will be 1. So that's a very interesting thing, isn't it? All right, the next thing we want to consider is the use of a negative. We're at 0, so what about if we go a to the minus 1? Now, what's jumping off at the page? What's jumping off the page at you? What's the information information in the equation. Now that's maybe never been said to you, but in terms of, I'm just going to put expression or equation. So I'm going to go back to my strategic one there, and I'm going to do that. Information. Look at all the things we need. Information in expression or equation. So what is the information? Well, the minus means something. The minus index means a reciprocal. So that guy there means this. And what you'll notice is that it's a replacement. Okay? The minus index gets replaced, and vice versa if you go the other way. So that one gets replaced, and we end up with 1 over. So we'll still get a to the 1. Notice there's no minus sign. Okay? So how would we do 1 to the c? Another way of doing that is to replace the reciprocal with a minus. And it had a 1 as a power. Dun, dun, dun. Okay, so anything that's there okay. Now the b, I've just written the same thing there. That's not helpful. I was wanting to make that something else. So 4d divided by b3. So in this case here, the way we want to think about it is that hidden in all of that can be written a reciprocal. Okay, it's just a times, isn't it? It's a times, an imaginary 1. Okay, 4d times 1 is 4d tick. b3 is times 1 is b3 tick. Okay, so what we can do is we just treat the reciprocal as if it's affecting the b cubed only. So 4d, they're not affected. So the b now comes up. The reciprocal has disappeared and been replaced by the minus sign. Okay, so that's our answer. That's all we need to express in terms of using our reciprocal. So there's lots of different times that this appears, and just watch when there's numbers, what's actually involved in the reciprocal and what's not. So that's that step. All right, so the next thing we'll consider is a fractional indice. Now, it's very interesting to write something like this because I can start off doing this the traditional way, but students get lazy and don't really cognate what's going on. A fractional indice, and they're in the laws that I showed also, represents a radical. That's called a radical. It's not a square root sign. A square root sign is a radical with a second base. Okay, what sits in the nape here is the denominator, and so the power sits. So that's actually the form. That's actually the form that we use when we're comparing these two things. Now we can go back and be lazy bones, okay, and say that the denominator, the nape has a 2 in it. So the denominator will have a 2. The a has a 1 in it, so the numerator will have a 1 in it. So this exchange of information, this use of ideas is very, very important. Okay. So now we should be able to do lots and lots of combined things to make life interesting. So let's have a look at a combined one. Let's do a to the minus a third. Wow. A to the minus a third. Now there's 2 pieces of information. 2 pieces of information. One is the reciprocal and one is the fractional indice. The minus sign tells us the reciprocal. So the minus is being substituted, so we no longer need it. The fractional indice tells us there's a radical. Oh, very good. 3 sits in the nape, so it's the cube root. It's the cube root of a to the 1, which is just the cube root of a. Very good. Okay, fair enough. We've got all that. So I can put that together now and use that. Okay, so if we go back to a slightly more complicated code 1, I'll do a code 1, which we kind of recognized as, so we're going to take indice out the front, index out front, and subtract 1 from the index. So before we get going to do something like this, what we'll see is that there's a fair bit of pre-work to do. So y is a function of m, not x. I'm just being annoying deliberately, but there's pre-work to be done. So first of all, we can make the radical go away, and it's a square root, isn't it? So it's m to the power of a half. The next thing we can do is we can make the reciprocal go away by putting minus a half. So we've transformed it. We've made it from one form into another. That's going to be very helpful in the next stages. So what we're going to do is do the index out the front, so minus a half out the front. Then we've got m, subtract 1 from the index, so we had minus a half, minus 1. So immediately we've got ourselves a thing we've got to attack. So minus a half, minus 1 is not the same family. What is the family that's going to support this in the form of 1? 2. So we've got minus a half, minus 1, minus 2 over the family of 2. So that'll be minus 3. If you're not sure, go to your number line, go to minus 1 and take 2 away. So we've got minus 1, minus 2, minus 3. That's where we landed on. So minus 3 on 2. So all of these become minus a half m to the minus 3 on 2. So we've done our gradient function, or code 1. Okay. Now to get that back, this is why people get caught up in this level of work, is that we've got a reciprocal. So we're going to get rid of the minus and make the reciprocal. One bit is the 2 that was here, tick. Now the 3, m3 on 2, m3, no minus, gone. That minus is there because that's that minus. That minus is gone because it's been replaced with the reciprocal. That was a replacement, like for like. So we've still got the minus part of the equation. We've got our reciprocal. Now we've got the square root, the denominator, m cubed. So without too much drama, you can cause a lot of drama with algebra. These are the gymnastics that I think cause problems for students when calculus comes along. Algebraic gymnastics. So I think that's a big part of what happens to you when you're learning to survive in university level mathematics, whether at school or elsewhere. All right, so we could just quickly do an integration, same kind of thing. We'll just do 1 over the square root of x. We'll do it that way, function of x. So the pre-work is that we can have x to the half on the bottom. We'll get rid of the reciprocal. So we bring that up as a fractional indice and add in our minus. So that's the informational aspects of it. So now we can go and put our plus 1 divided by 1. So we've got x to the minus a half plus 1. So I'll just get rid of that because that was just that's pre-work. I call this bit here, this transformation, I call that pre-work. Okay, that's your pre-work. And then minus a half plus 1. So we'll go off and deal with minus a half plus 1. Okay, just get a habit in leaving something off. So minus a half plus 2 over 2. Now it's going to be different, isn't it, to what we did before. So minus 1 plus 2. 1, 2 is going to bring us up to plus 1. So we've got just a half. So this is x to the half divided by a half. And I'll just go the long way with that. X to the half divided by a half is x to the half times 2 over 1. So we get 2x to the half, and finally we get 2x to the half is 2 times the square root of x. So that's our integration, and if it is an integration up and under, then we'll put a plus c on it. Okay. So the gymnastics that we use is considerable. All right. All right. After this, I'm going to have a look at some linear graphs. So I'll be back shortly.